All right, this is the spreadsheet that my father and I created over a long period of time for calculating spoke lengths. It does more than that. It will also calculate what the total cost is and what the estimated final weight of the wheel building project will be. So we're getting ready to do a new project. So I'm going to clear the front, no data there, and we're going to be clear the rear. And then I've got this macro I got my dad to create, rear wheel only. And it's going to prompt me step by step for the data that we need. Set it up here, sir.
Okay.
First thing we're going to get is what's called the OLD, the overlock nut dimension, which is just the axle width.
Okay.
This old TS3 wheel throwing stand is like the perfect tool to be able to measure these giant motors with.
All right.
And I'm measuring it 134.1 millimeters.
Okay.
Put it back.
Put it back in the stand.
Correct.
Okay.
And I want to show you so that if you end up ever needing to do it one day,
Okay.
the actual dimension that I want is from here to the middle of this flange.
Gotcha.
But there's not any easy way to measure directly from that to here. What I can measure is from here to here.
Right.
And then offset, I know what that dimension is, that's 5.5 millimeters.
5.5.
That's offset.
Okay.
So, and this is actually not a super critical dimension, so I usually just try and eyeball it and get it to the nearest half millimeter.
Okay.
And that's probably way more precise than any wheel builder ever actually really needs to do it. So that's 56.5.
Plus 5.5, you said?
Correct.
Okay. So 51.
51 millimeters.
And what dimension do we call that?
It's the A dimension, which I can't show you because this macro is running. But it's actually got a diagram down here that shows you what those dimensions are.
Okay. And in our case, the A dimension is from the disc brake side, axle to the left flange.
The left side.
Left side. Yeah. Okay.
Now, to be able to measure it easily, I usually always measure the left side. So I'll flip it around in the truing stand.
Okay. To do the right side.
Correct. Still making the same type of measurement.
Gotcha.
Wow, this would be a highly symmetrical wheel. Nice. Cool. 55.5 minus 5.5, that makes it 50.
50. So 50 on the right side, 51 on the left side.
Correct.
Okay.
What's most common is usually the left side is a whole lot more off to the left.
Mm-hmm.
Okay, and then spoke circle diameter.
Okay.
This is what I actually bought these for. And I believe that the dimension that's specified on the Muxus drawings is 231 millimeters for the spoke circle diameter.
Right.
And I don't know if I've told you or if you remember, when I've been measuring it of late, it's actually been 232 millimeters. 100, 200. this is a fairly important dimension, so it's important to measure
Right.
it as accurately as possible. That's 232. This one looks like it might actually be the 231 dimension.
Okay.
Yeah. So, good thing I didn't just assume it was going to be 232. The vast majority of hubs, these dimensions are almost always metric.
Mm-hmm. Because they're made in China.
It's because the rest of the world, except for this country, is metric.
Yeah.
Metric system is a better system. I will be so happy when the barbaric antique English system dies.
Yeah.
And it is possible to have two different spoke circle diameters on the left and right, although on these Muxus motors it's almost always the same on the left and the right.
Right.
This one it is 231
Okay.
millimeters.
231.
3.5. I'll go with 3.5.
Okay.
And now it wants to know how much that bugger weighs. This should be sort of fun. You get to see how I actually weigh a wheel.
Yeah.
This is the official Muxus motor holding tool. I tear it out. I don't want pounds, kilograms. Tear. Okay, this ready. And 7,640 grams.
7.6 kilos.
And the number of spokes, 36. The number of intersections, 1. Number of intersections, 1.
Single cross.
Yes. Have to use single cross with these giant motors.
Okay.
But this gives us the main numbers that I wanted out of the deal, which is the spoke lengths.
Okay.
It says 162 millimeters. And we'd preferably want to build with 2.3 millimeters or even 2.6 millimeters.
Okay.
162. I think what I've got is 163.
Okay.
The spokes may be upstairs. But that's the main number that I needed out of it to begin
Okay.
with.
Okay. Those guys right there. All right. So what type of spokes are these?
These are Supreme stainless steel spokes.
Okay.
The model is called the Strong.
The strong.
And what that means is that the J-bend end of it is 2.3 millimeters in diameter up to here, and then it butts down to 2 millimeters for the remainder of its length, with 2 millimeter diameter threads with the weird bastard mix of English threading.
Gotcha.
56 threads per inch, wide threads per inch.
So some wheel builders might call this a 12 gauge 13 gauge or 12G 13G spoke. If you're going by those designations.
I don't honestly know. Every time they try and say it, I find it confusing.
So you like to use 2.3 or whatever the millimeter dimension is.
Yeah, exactly.
Yeah.
And the reason why is because there's been 10 different wire gauge systems that have been defined. Some of them are no longer in use, and not a one of them matches the diameters of spokes.
Okay.
None of them.
Okay. So 2.3 butted down to 2.0.
Correct.
Okay, and these are the 163s?
These are 163, correct.
Okay, that's a lot of spokes there.
It is, because we need it for lacing with those things. And I was thinking I'd let you have the honors of doing the lacing. So
Okay. I'll be the guinea pig. It'll be the proof that any idiot can lace a wheel.
Well, I wouldn't phrase it that way, but okay.
All right.
I
So-
typically like to put the freewheel side down,
Rear wheel side down. Okay.
and
Is that because of the way the cable exits, or is that just
I guess that's probably the main reason why.
okay?
And anytime that you're going to be lacing a wheel, you're going to be doing it in 4 sets of spokes. And when you put the very first spoke in, it needs to start with one of the spoke holes right next to the valve stem, always.
You
without
want to
fail.
angle away from the valve stem.
Exactly. So you're going to be lacing it into that hole,
Okay.
and it's not going to matter which of these holes that you pick. The only thing that it's going to affect is if we were trying to cosmetically align
A logo.
a logo on it, we could try and pick one particular hole. But
Okay. If we were trying to cosmetically align a logo, how would you do that? Let's say we wanted to align this serial number as the logo.
Okay. Well, what you do is you get the logo, because it's just one cross, that makes it fairly easy. Here's the dusting hole right here. I mean, it's gonna be going here, and it's gonna be crossing over this way, just one, on
Okay.
the opposite side. And so it's gonna be probably like this hole.
Okay.
And when you put the hole or spoke from the inside to the outside, this is what's called an outbound spoke.
Okay.
And unlike most of our motors, where we do all the spokes outbound on the right flange and inbound on the left flange, on a wheel that's very highly symmetrical, like what this one is,
Mhm.
plus these flanges are relatively thin, we're gonna do more like a regular bicycle wheel, where we will alternate inbound, outbound, inbound, outbound.
On each flange.
Correct.
Okay.
And what you need is oil for the nipple.
Okay.
Which is going to be more convenient for you to have the stuff sitting over here or over there.
Probably on the right. So what kind of oil is this?
That is Fillwood tenacious oil, which is a very high viscosity oil. It's got an extreme lubricity factor, which I like real well.
Okay.
And what you need now is it's going to need to go into this hole.
Oh, that hole. Okay.
And
So
then
is it
thread the
gonna
nipple.
cross? It's going to cross that way.
Correct.
Gotcha.
You will be using this tool for putting the nipples on, but you don't need it yet.
Okay.
You did put oil onto the threads, right?
Yeah.
Okay.
And I pre-thread till about 3 millimeters to the end of the thread.
No, more like about 1 to 2 millimeters.
1 to 2 millimeters.
Yeah.
Okay.
Especially since this spoke is a shade on the longish side.
Okay.
Won't cause any problem for our wheel
And
build.
then this rim has single wall eyelets.
Yes, that rim has some wall eyelets on it.
Okay.
And you notice that when we selected this, I selected this one. I told you which one to do it.
Mm-hmm.
A lot of times the eyelets are going to be offset to one side or the other,
Right.
and you want the offset to match the side of the flange. So this
Gotcha.
this
So
eyelet is offset down,
right. Gotcha.
so we want it to go with this one.
Okay. Yeah. I can just barely see a slight offset there of the eyelets.
And sometimes it's hard to see. What you have to do is you actually have to look through the hole from this side, and you
Okay.
can see the angle of the hole drilled one way or the other.
Right. Okay.
So what you want to do now is you want to rotate the motor a little bit,
Okay.
and you're going to be going to, you skip one hole
Skip one hole.
and go to the next hole.
Okay. And then go down again. So since I'm alternating, if I'm skipping, I'm going to go down again, outbound.
Exactly. When you're doing the first set of spokes, you're going to do half of the spokes on one flange.
And then I skip 4.
Well, you want there to be 3 empty holes and go into the 4th hole.
Okay.
Now that will always be true, even if you're doing different spoke count wheels, 32 spoke, 28 spoke, 24, 20, 18, whatever it might be. Did you put oil on the threads?
I did.
Okay.
Okay. Alright. Repeat. Skip a hole. The lube. And skip 3 holes, go to the 4th.
Correct.
So we're lacing this as a 1-cross pattern. Sometimes when you have really small diameter rims, people want to lace those radially. Why would you not want to lace a wheel like this radially?
Because of the torque transfer from the hub to the rim. Anytime you have torque transfer between the hub and the rim, whether it's because of brakes, or because you've got an electric motor, or because the hub actually has gears on it, if you laced it radially, the spokes are not going to be able to effectively transmit the torque to the hub. It's going to greatly increase the tension anytime torque's applied between the hub and the rim. And it'll end up fatiguing, especially the heads of the spokes, and the spoke heads will eventually break if it's laced radially. So you should not ever radially lace a wheel where there's torque transfer between the hub and the rim.
Okay.
In general, it's usually preferable to have a higher crossover pattern, but you can't on these because of what the difference in diameter is. It's a relatively big diameter hub and small diameter rim.
Right.
So the most crossover that we can get is 1. If it was a smaller diameter hub, we could do up to 4 crosses on it with a 36-hole wheel.
4 cross gets you pretty close to a 90-degree angle to the hub, right?
4 cross would make it a perfect tangential lacing.
Which is ideal.
Which, yeah, ideal for torque transfer. It'll make the spokes the longest. So the weight wings of the world would have heart palpitations.
I noticed the spokes tend to bend a little bit as you're kind of forcing them in place.
Yeah, that's okay. These spokes are very highly fatigue resistant. They have to be. There will be things that we do in the process of building to reduce the likelihood that fatigue will be a factor in whether or not the spoke will break or not in the surface of the wheel. It shouldn't. An ideally properly built wheel will not have spokes break from fatigue.
Okay. Alright, so there's the first set. So now which set would I want to do?
Well, there's 2 ways that can be done at this point. I'm going to, because I think it'll be easier for you to visualize and perhaps others as well. We're going to do both sets on the same flange, and then we'll switch over to this one. It makes it a little bit trickier doing the 3rd set of spokes on this flange, but it does make it less likely that you'll get the spokes that you start over here installed incorrectly.
Okay.
What a lot of builders will do is they like to get 1 set here, 2nd set here, and then you can do the 3rd set on this side, and then the 3rd and 4th set over here, which does have advantages, but if you can't properly visualize how the spokes go and get them started in the wrong hole, and end up burning a lot of time to undo it and redo it.
Okay.
So
all these are going to go.
don't start yet. Hold on a second. I got to tell you what to be able to do. Find your valve stem hole and get it over here.
Okay. Right there.
All right. Now, we know the wheel is going to be this way because we want the spoke to be angled
Right.
away
So
from
we
the valve
want
stem
this
hole.
spoke to be over there, right?
There No, remember, it's gonna be every other hole.
Okay.
So you can start in either one of these holes, and right now you've just got the wind up. You're going to want to do inbound lacing.
Mm-hmm.
And on a regular bicycle wheel, we would actually cross this spoke underneath. Because of how thick these flanges are, don't generally do that.
Okay.
And it's going to go here.
Okay.
At this point, you're going to need the special nipple installation tool.
Gotcha. Okay.
And what I usually do is I install the nipple onto the tool. And all you need to do is just get it started. So this first one can be a little bit tougher than some of the others. You have to try and get as much of the wind up out of the way as possible.
Mm-hmm. What do you call that tool?
This is made by a guy down in Vancouver, Washington. And I don't remember what he calls it. I can't remember what he calls it. I like that tool, but there's a lot of different tools similar to it as far as their functionality.
Mm-hmm.
And what you will need is you'll need a nipple spinner.
Okay.
Because at some point in time, the nipple will just barely get started.
Okay.
Any observations on your part about the assembly so far?
Pretty straightforward. Once you figure out the first one or two, then it becomes pretty much just a exercise in repetitivity. Okay.
All right.
So my
So hold it up to show the camera what you've got so far. You've got the right side laced.
right side is laced.
Getting ready to do the left side.
Getting ready to do the left side.
So for the left side, again, locate your valve stem hole. That's your
Okay.
starting point,
Yeah.
always.
Yep.
And this time, you're going to be getting the first spoke that goes from here, the hole right next to the valve stem hole, out to the rim. And it's going to be parallel to this spoke. So that
Okay.
means it's going to be inboard one. So it's going to go from this hole
Gotcha.
to that one.
Okay, and it's inboard.
You want this to be mirror image lacing. So
Okay.
because it's going to be parallel to this one, you want it's going to be like that one, it's going to be inboard, inbound, other way.
Oh, this way. Okay.
Yes. And this is what makes this method of lacing a little bit more cumbersome, is sometimes trying to get the spokes clear around the other ones is a pain. Fortunately, this particular wheel build, not going to be a
Okay.
problem.
Okay.
Oh, and the name that the guy makes for that particular tool is called the MULF, M-U-L-F.
MULF. Is that an acronym for something?
I think it is. I don't remember what. I don't think it actually says in my tool catalog. MULF mill finger, I think is what he calls it.
Mm-hmm.
Before you lace any more spokes, show to the camera how you've got this one particular spoke relative to the valve stem hole. You might even want to take that close to the camera.
Okay.
So there's the valve stem hole. Here's the spoke that he just installed. It's parallel to this spoke. This spoke is inbound, so this spoke is inbound as well. That makes it mirror image lacing.
Okay.
And now you just want to do like you did the other side.
Skip a hole. And over 4 holes, right?
Exactly.
Okay. And it's generally always going to be parallel to the spoke on the opposite side.
Yeah.
Alright. There's the third set of holes. And,
It's easy at this point.
okay.
It's going to be outbound, crossover. Like I said, because of these thick flanges, we're not going to actually physically cross it over and under the spokes.
Right. So if we were doing maybe a smaller hub with a 2-cross or a 4-cross, what would be different about the way that we do this?
Not a whole lot, other than when
Just how many holes you're going over?
Yeah. The spokes would be
Longer?
longer,
Yeah.
and if it's a smaller diameter hub, we're probably talking about a conventional bicycle hub, which has thinner flanges, at which point, when you have 2-cross, or 3-cross, or 4-cross, the last crossover point, you want to physically take it and cross it under. What that does is it helps equalize the tension throughout the wheel.
Okay. You want to talk a little bit about bracing angle and how that relates to
The strength of the wheel.
the strength of the wheel?
Be easier to show it. And this is where the hub is going to sit against the frame
Mm-hmm.
on the right side, and this is where it's going to sit against the frame on the left side. Most rear wheels, there's going to be a difference in spacing from the right flange and the left flange.
Mm-hmm.
Right flange is usually moved in a lot more than the left flange is. And the bracing angle is the angle from the center of the hub to the center of the rim. The steeper it is this way, the less of a bracing angle.
Right.
The more out this way, the better of a bracing angle. Ideally, if you can actually have the angle on the right and the left, the bracing angle be the same, it'll give you equal spoke tension, it'll give the wheel better strength overall. This wheel is actually almost perfect as far as its equal bracing angles, so
And
that's
then
good.
that has to do with the distance from the
Where-
the
where-
act
From where it sits against the frame to the flange.
to the hub flange. So it was almost perfectly centered.
Yep.
Do you recall off the top of your head what the difference is when we do our fat bike wheels, what that difference is?
I don't, I would have to look it up, but
It's more, it's quite a bit, right?
yes, it is.
This part seems pretty straightforward. Once you know the basics, it's very repetitive, and
Yeah.
I can see what you mean by being able to watch TV or something like that while you're doing something like this.
Yeah. You've done thousands of them, sure. The main difficulty that most people run into is you have to make sure that the very first spoke goes in the correct place, which is, it's got to always be one of the two holes right next to the valve stem.
Okay.
And then you need to make sure when you lace the second flange that the two spokes are going to be as close to parallel, maybe slightly divergent.
Mm-hmm.
And that just makes it where it's going to be easy to get to the valve stem.
Right.
I have seen some people that when they lace it, they don't pay attention to it, and the valve stem may end up being between two spokes like these that are
Right.
coming together, and you can't get a pump head onto the valve stem in a case like that. That's
Right.
why you want to have the valve stem, but the spokes are going to be close to parallel or slightly divergent.
Mm-hmm.
And we're going to also show the complete truing of the wheel as well.
Yeah.
Okay.
Last spoke.
Right, you don't need the spoke collection anymore.
All right. So we have a laced wheel that is not yet tensioned or trued.
And we will be wanting to put that onto a Park TS 2.2 wheel truing stand.
Let's talk about the stand first
Okay.
and what features it has.
There's a lot of wheel truing stands out there, especially if you're going to be building wheels with these heavy motors. You want something that's got good, strong support arms on it. The Park Professional Series, currently the 2.2 and the 2.2P. Exact same creature. And that one's a little bit less expensive because they powder coat it rather than chrome plate it. But it is self-centering, which is very, very nice. I've never yet actually seen one of these stands come from the factory though, where it's properly centered. What you have to do to make sure that it is centered is it's got these two collars right here. And they have to be loosened. And then you have to make sure that these arms, after these collars are loosened, I have a metal plate that I'll put from here to here. I'll make sure that these arms are exactly the same.
Parallel.
Because once you loosen these, they'll go back and forth like this.
Gotcha.
Once you get them centered with this part of it, lock the collars down, and now you want to center the touch probes. And the easy way to adjust these touch probes, you can actually do it with a regular bicycle wheel. Just have to make sure that
It's a good bicycle wheel. well
it-
trued.
It doesn't even have to be well trued. It just have to be no loose hub. It's got to be properly adjusted hub at the least. It can be wildly out of true at the end of it, but you're always going to be using where the valve stem hole is.
Gotcha.
What you do is you put the wheel in up here, and you can flip it back and forth
Gotcha.
to see which way you need to move the arm. And all you need to do is just tighten and loosen these nuts right here, and that will move the whole arm assembly. Once these are centered here, and then this is centered as well, it's a total self-centering mechanism. You don't have to do like a lot of mechanics do, where they just use one probe at a time and then flip the wheel around the other way, which is immensely time consuming. You're ruining the advantage of actually having a self-centering truing stand.
Okay.
And what I see a lot of mechanics do when they put a wheel into the truing stand, they use these like vice grip, like a vise. It's not a vise. it's simply a touch tool. This is spring-loaded, this is spring-loaded, that's spring-loaded. If you actually try and use it as a vise, it's going to distort unequally, and you're getting rid of the self-centering feature. So all you need to do is just get it to the point where it's gently touching. Because we've got this giant electric motor, there's one extra thing that we'll have to do to keep the motor axle from spinning. But open it up. I like to always put the wheel in the truing stand the same direction as it would face as if I was sitting on the bike. So left side on the left, right side on the right. Tighten it down. And like I was just mentioning, all you need to do is get it gently snug. The problem with our electric motors is
There's resistance in the axle.
there's resistance in
And
the
the axle isn't perfectly round, it's got flats on it.
Yeah, and so we have to do something to keep that axle from rotating. These flats are 10 millimeters. All I need is a 10 millimeter wrench. And I get the flats,
Horizontal,
well, perpendicular to the arm.
right.
And then I use axle nuts and washers to hold it in place. And I don't have to tighten it down a huge amount. It just needs to be
Snug,
enough friction to keep that axle from rotating.
right.
Incidentally, and you can spell this out, tell
Yeah.
people about what happens if they get the wires touching.
Yeah, so if the wires have bare ends or even connectors and the connectors touch together, then what happens is you're essentially shorting the phases in the motor, which acts like a motor brake. It's kind of the same effect of regen braking if you're shorting all three phases together. So if those three wires are touching, it'll be immensely more difficult to turn the motor, the axle within the motor. So as you're lacing it, it's best to maybe turn one of the couple of the wires different directions so they don't actually, the wire itself is not touching the phase wires. That'll make it much easier to rotate.
Yeah. And now, because we've got this nut on there and it's just gently snugged down, the motor will turn, but the axle does not. I don't need to put it on the other side. This is a touch mechanism. I am not going to be straightening the wheel by beating it into shape, which is what I think some mechanics think they have to do. Now, as a general guideline, if you have the right length spokes, most of the time, when you tighten the nipples down to the point where the threads are just disappearing, then it's either close to start getting a little bit of tension, or it may have a slight amount of tension. It's going to be seen right now.
Right.
Very, very little tension. So I'm going to be using the nipple spinner
Okay.
to snug the nipples down a little bit. And always start where the valve stem hole
The valve
is.
stem.
And I just tighten it down to where the threads just disappear. And that will give me equal engagement.
Okay. And you're just kind of bending those spokes so that they exit straight out of the rim. Makes it easier to.
This is a double wall rim. What that means is that there's what's called a web on this side of it. And if I tried to put this nipple spinner in there at this angle, it's going to be hitting against that web.
Gotcha.
So I straighten it out so it's going to be closer to perpendicular.
Mm-hmm.
And that allows me to be able to get the nipple spinning tool in so that I can more easily
Right.
spin it down.
Okay.
You don't have to have a nipple spinner.
You could just use a straight screwdriver.
You use just a straight screwdriver. This one I actually bought from Craftsman because it's got diamond powder coated tip on it, which allows it to have a friction
Stick
fit
better.
to the tip.
So just a kind of a close up of the nipple spinner here. It's got a little bit of a
Nub.
point or a nub on it that kind of seats itself in the
Center
nipple
of the
itself.
nipple. Exactly. And alternatively, if you don't have a screwdriver that'll fit, you will need a spoke wrench. So you can just use the spoke wrench. This just makes it a little bit faster.
More efficient.
If in the process of spinning the nipples down, you get past the halfway point and the nipples are starting to get really, really tight, it probably means the spokes are too short.
Okay.
Again, just as a general guideline, the nipples should be just barely starting to get a little bit of tension on the wheel if the spokes are the right length. If you tighten them down to where the threads are just starting to disappear.
What's our variability as far as spoke length? If you calculate, say, a 162.5 millimeter spoke length and you have a 164, is that going to be close enough? How exact do the spoke lengths need to be to whatever you calculate?
Well, if you're using brass nipples, brass is very strong. And you can have the spokes be equal to the spoke length that they should be. They can be actually short by a millimeter, and it shouldn't cause any problem.
That relates to like thread engagement and strength.
Thread engagement and strength, yes.
Yeah.
If the spoke is too long, then it's possible that the spoke nipple might bottom out on the spoke, and you won't have adequate tension. I know with these particular spokes, even though they're a little bit on the long side, ideally the length would be 162 millimeters. We're building with 163 millimeters. These nipples will actually go past that. I'll have 100% full engagement. It just means that the spokes are a shade on the long side. It doesn't cause a problem because these spokes will not bottom out if they're just 1 millimeter too long. The time it's most critical is if we were building with aluminum nipples. Aluminum nipples are very, very sensitive to the correct spoke length.
Okay.
If you want it to be a good durable wheel, but we're not going to be building with aluminum nipples on these electric motor
Okay.
bikes.
And these are brass or stainless nipples?
They're brass.
Brass.
They're nickel-plated brass.
Okay.
Okay, so now I've got the nipples all down to the same length. There's still a lot of slack. We already know that these spokes are a shade on the long side, so now that I've got them all to the same spot, I'm going to go around and I'm going to tighten it down an extra full turn.
Okay.
Usually at this point I will actually use the spoke wrench.
Okay. Now, just to remind everybody, so the butt end, or actually the nipple end is 2 millimeters. And so these are 2 millimeter nipples. And what size of spoke wrench are you using on those?
The threads are 2 millimeters in diameter. The flats on these nipples are 3.2 millimeters, which if you're using a Park spoke wrench, it's going to be the black handle spoke wrench.
Okay.
There's a lot of other spoke wrenches out there that are equally good quality. The Park spoke wrench is very easy to find just about anywhere, either in local bike stores or online if you want. It's got a good quality fit. It is important.
Just do one full turn on each one.
Yeah, the important thing is to very gradually get the spoke tension to go up. And what I've seen some people do if they're doing their first wheel build is they'll want to try and start pulling up tension on the very first spoke. You can't. Spoke tension has got to very slowly increase, one spoke at a time. Right now these spokes don't have any tension on them, so I'm just trying to get to the point where they will just be barely starting to get a little bit of tension. Once they're at that point, that's when I'm going to be able to actually start to tension and true the wheel at the same time. So initially what I was aiming for is to just get the nipples all the same amount of thread engagement. Now I'm trying to get it where
They still have the same thread engagement, but now they have a little bit of tension.
well, hopefully. I know it's not going to actually start to get thread engagement because these spokes are a little on the long side. These are actually very short spokes compared to what are used in most bicycle wheels of this size.
Right.
And that's because of the large diameter of the
Motor hub.
hub. And so one full turn, it still hasn't even begun to get any engagement on it. So I'm going to go around and do one more.
And you always start at
With
the
the valve
at the
stem.
valve stem.
That's the start and stop point for just about everything. Makes it easy to keep track of where you are.
Yeah.
One advantage that these electric motors have as compared to a conventional hub when you're doing the build is if I need to stop and go somewhere, whatever reason, I can stop right here and I know that I left right there. This thing's not going to spin, whereas a regular bicycle wheel is low enough friction in the hub, the heavy spot's going to rotate down to the bottom.
Mm-hmm.
So I would lose track of where I'm at. You need to keep track of where you're at. The whole idea is to try and do all these spokes same amount.
Until you get to the point where you're truing the wheel.
Exactly. Once I get to the point where I'm starting to get a little bit of tension on the spokes, the first thing I'm going to be doing is I'm going to be truing it laterally, which is side to side.
Mm-hmm.
And then I'll be truing it radially, which is in and out. And for some people it might be kind of boring because you're just basically going back and forth between truing laterally and radially, laterally and radially until while you're doing it the spoke tension slowly increases to where it should be at.
And
Yeah.
getting a good, strong wheel build is all about having the right tension, having enough tension.
High tension preferably.
Yeah.
As a general guideline, the main limiting factor on how high of a tension that you can have on a wheel is determined by the rim.
How strong the rim is.
Exactly. And as a general guideline, what you want to do is to get the tension high enough where the rim is almost at a point where it's going to collapse.
Taco.
Yes. From the attention of all the spokes on it. That will actually give you the best durability, is where you have nice high tension like that. And the rims that we generally build with for these electric motors are very heavy, beefy, strong rims.
Mm-hmm.
So I can pull very, very high tensions with these, which is good, makes it more durable. That's one difficulty with these wheels though, compared to a regular bicycle wheel. A regular bicycle wheel there are tools that you can use to measure the spoke tension. And what it's going to actually do is it's going to create a deflection across 3 points on the spoke. But these tools won't fit onto these little stubby short spokes that these wheels are built out of.
So you just have to kind of go by feel as far as tension, or maybe by the sound if you pluck them.
Well, the sound can work if you're building the exact same type of wheel all the time. The sound is going to be like a piano. It's going to depend on the length of the wire, the thickness of the wire, and the tension of the wire.
Mm-hmm.
All those factors. So I would have the exact same tension on these spokes and another wheel that's got much longer spokes, but the plucking the spoke would sound different between the two because the thickness of the wire and the length in particular.
Mm-hmm.
So
But as far as maybe them being very similar in sound on a given wheel.
well, you want the spokes to sound similar to each other.
Mm-hmm.
In other words, approximately equal spoke tension from one to the other.
Right.
And how equal the spoke tension is going to be is dependent more than anything else on how good of a quality of the rim. If it's a poor quality rim, it's not what I would call round.
Mm-hmm.
And that means that it's going to have highly variable spoke tension on it. Probably the worst wheels that I've seen are bicycle wheels that have steel rims. They're not round, and the spoke tension is very highly variable on those.
Mm-hmm.
So I did yet another round, and it's just barely starting to get a little bit of tension on it now,
Okay.
which is the point where I want to start. And first thing I'm going to be doing at this point is the lateral truing. The lateral truing, it's touching on this side between these spokes.
Mm-hmm.
So that means that I want to pull it over that way.
Okay.
These are long, skinny screws and nuts, basically. So that means that I'm gonna tighten the nuts or the nipples on this side and loosen them on this side in order to be able to move it over.
Okay.
So tighten, loosen, tighten, loosen, tighten, loosen, tighten, loosen. And it didn't move it a lot, but it has moved
Improved.
it some.
Right.
And I just keep moving the probes inward until I find those points where it's touching. And it's touching across these 4 spokes, so I'm going to tighten and loosen. So starting here, tighten, loosen, tighten, loosen. I'll go beyond the point where it's touching. How much you may need to do is going to vary during the process of the wheel truing and tensioning.
Okay. And when you're tightening and loosening, you're only doing a quarter turn?
Yes. Again, this is a project where you're just trying to make very small changes. You want it to slowly build up to what it's going to be. A wheel ideally is going to be round when it's done.
Mm-hmm.
And it's ideally set up to be able to accomplish that. And this wheel is different than most rear wheels would be, because most rear wheels the rim would be offset to one side or the other. And I wouldn't have to spend, I would have to spend more time getting the wheel centered initially.
Mm-hmm.
And this one's already reasonably nicely centered. So, having done those very minor amounts of lateral truing, I'm now ready to do the radial truing. And this is the part of the operation where the spoke tension is going to slowly be increasing. So what I do is I get the probes close, and I want to slowly increase or slowly decrease the distance between the probes and the outside edge of the rim until it just barely touches. And it's touching across these two, so I just want to tighten these two.
Mm-hmm.
That's going to increase the tension. It's going to take this high spot and pull it in.
Mm-hmm.
And the tension across the whole wheel is going to be sort of like a piano. If a piano tuner was tightening the wires in the piano, if he tightens one wire, it's going to increase the tension across everything. The same thing's true here. It's going to have the most noticeable effect here,
Mm-hmm.
but it's going to be slowly increasing the tension everywhere on the wheel. And again, I just do a quarter at a time.
Okay.
And it's still barely touching, so turn it in a little bit more.
And you do 2 of opposing spokes,
It depends
so
on...
it stays relatively true laterally?
No, I'm mostly concerned about just trying to get it radially true. If it was touching across these 3 right here,
Mm-hmm.
I would actually go ahead and tighten these 3. That'd be 2 of them on the left side and 1 on the right side, so it would tend to
Pull
the
it to
wheel
the one
off
side.
to the left. But I'm more interested at this point in just
Getting
trying to
the
get it
radial true.
Radially true. And in the process of making it radially true, it's going to be increasing the tension. Again, it's touching on these 2, so increase tension, increase, and increase. And what some mechanics will do is they'll try and increase the tension on all the spokes all at once, and then try and let spokes out and let spokes in. And it makes it actually more time consuming in my observation of mechanics that do it that method. Now notice it's touching across these 3.
Mm-hmm.
So even though that's going to pull it off to the right some, I'm going to tighten it there. Problem with doing the method where you try and increase and decrease is I haven't seen any mechanics yet. I'm sure there are somebody somewhere who can succeed in making the wheel nice and radially true. You should be able to get the wheel where it's true radially to within about a ½ millimeter without any great degree of difficulty. And most mechanics that I've seen do it the other way, the wheel ends up being radially out of true as much as 2, 3, 4 millimeters. A lot. Just touching across those 2, so I increase. Because what's happening is I increase the tension here is it's increasing the tension everywhere. And spots where it was sitting low, it's going to be slowly pulling them out. This method works very, very well at making the wheel not only radially true, but it'll have nice equal tension. And just slowly increasing the tension. Incidentally, speaking of wheel truing stands, there is a new wheel truing stand that was announced by Park Tool Company at Interbike this year. It's going to be the Park TS-4. And you'll notice now it's touching across all of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 spokes. And I will increase it 1/4 turn tension across all of the spokes. The TS4 wheel truing stand was specifically developed to work on fat bike wheels. And because a lot of the wheels that we build are fat bike wheels, it will be a tool that we will acquire once it's available.
Does it just have a wider jaw?
It's got a lot of things that they've changed on it. It's not quite as radical of a wheel truing stand as this vintage TS3. It's still the same basic idea as what this one is, but it's just designed where it will accommodate very wide axles, very wide tires. If we had a fat bike wheel and tire on this, the fat bike tire could not fit down between these uprights. It would jam. The only way that I could work on a fat bike wheel on this is I'd have to take the tire off.
Right.
Do you think the sound of the probes touching will pick up in that video?
Oh yeah.
Good. And when I first started doing wheel building nearly 30 years ago, I thought I'd be able to play music while I'm doing the wheel truing operations. And I was sort of sad to find out that I couldn't do it because I needed to be able to hear the probes touching. Maybe somebody else that has better ears. That's what I ended up having to do, though, is I I depend very heavily on being able to hear the probes touch. In order to be able to know where it's touching at. As it is now, the spokes are still pretty low tension.
Mm-hmm.
When I've got it where the spokes are all relatively equal tension and the wheel is relatively centered laterally and radially, I can go around and increase the spoke tension on all the nipples all at once.
Kind of like what we did in the beginning.
Yeah, except that I'm just going to be doing it very small amounts.
Just a quarter turn instead of a full turn.
Exactly.
So how many times do you go back and forth between lateral and radial truing?
It's going to depend on the particular wheel, but generally it's a pretty good bit. Just bounce back and forth between lateral and radial. Because right now the radial factor is just starting to get where there's a reasonable amount of tension on it. And now it's like pretty close to equal radial true. You want to see? You might be able to see it better. Well, whatever way works. Does that look good?
Mm-hmm.
Okay.
So now we go back to
lateral. And I don't expect that it's going to have gone out a lot because this wheel very nicely is almost perfectly symmetrical like a front wheel.
Mm-hmm.
Okay. So it's touching across these four. There's only like about 1 millimeter of gap, but the spokes are still under pretty low tension, so there's not going to be a lot of change. I can change those two that are in the very middle, these two that are toward the outside of the touched area, and it only moved it away about 0.5 millimeter on this side.
Mm-hmm.
I'm going to actually go beyond the touch area, an extra spoke on each side.
And then you just creep that in a little bit tighter.
Yeah, and this thing is, at that point, it's a rare creature as far as wheel builds go because it's almost perfectly symmetrical left to right.
Mm-hmm.
So I'm at the point where I've got pretty uniform tension across the spokes. The wheel is reasonably true radially and laterally. I want to just do an overall increase of the tension.
Okay.
I'll go around and I'll do 1/4 turn on each of the spokes until I have successfully done a full turn on all of them. That means I'll spin the wheel through 4 revolutions.
Gotcha.
And it will have gone through radially and laterally at that point in time. And I can go in and I can correct the radial non-uniformness in the lateral. And incidentally, if you need to take the rim off of the motor and you expect to, that's 1 turn, here's the valve stem hole, so this is going to be the second, so just 1/4 turn. If you needed to save the rim,
Mm-hmm. You want to unlace a wheel.
you want to unlace it, for whatever reason, If you want to avoid damaging the rim, it's important that you do the reverse of this in taking it apart. You very slowly detension it. If this wheel is under real high tension where it has like 200, 250 pounds of tension per spoke, and I either cut this spoke or I completely loosen the nipple here and completely loosen the nipple here, all these other spokes are under still real high tension. So what that's going to do is it's going to force the rim to bulge out and permanently bend it at that point. You would not be able to reuse the rim if it's done that way.
You're turning the rim into an egg, basically.
Yep. I know somebody that unintentionally did that, but they were not aware.
He who shall not be named.
But it's actually sort of a rarity that you'd want to take a wheel apart to save the rim. Usually the rim is a sacrificial member.
Right. Do you very often reuse spokes?
No. Spokes accumulate fatigue on them. And even though the spokes are, the manufacturers do a lot of things, and we do what we can in the process of building it to make it where the fatigue will not result in spoke breakage during the life of the wheel. Nevertheless, fatigue is accumulative. And it doesn't make any sense to try and reuse spokes in order to save money, especially on a front wheel. That's a wheel that if the spoke breaks, let's say you're going downhill at high speed and your front wheel should break on you, your life is in danger. You don't want to put your life in danger just to save the cost of money on spokes. And incidentally, one of the things that we do with our wheel builds, if we can, is we use spokes that are butted.
Mm-hmm.
The butting helps to increase the strength and the durability of the wheel. The majority of the stress on a spoke is on the J-bend head of it. And so the spokes that we use are thicker on that end.
Okay.
They don't need the extra thickness here. In fact, they need to have elasticity out at this end of it. It's not to save weight.
It's to give the spoke a little bit of spring.
Yeah, that'd be a good way to phrase it.
And is it better to have, in general, a larger diameter spoke or a smaller diameter spoke when you're lacing a wheel like this?
The place that's got a bunch of good information on the theory of wheel building is a book written by Joe Brandst, B-R-A-N-D-S-T, called The Bicycle Wheel. And he very correctly points out that you'll get the most durable wheel if you have a very stout, strong rim, similar to this one, with a relatively high spoke count, which this one has, and if you use very thin spokes. We don't want to use thinner spokes with this because of the heavy weight and torque that's going to be applied through this. But I have built wheels on tandems that were 36 spoke, 40 spoke, or 48 spoke, and rather than using spokes like these, which are 2.3 millimeters to 2 millimeters, I've used, like Joe Brandst did, very, very thin spokes. They'd be 2 millimeters on the end, and they would go down to 1.5 millimeters in the middle, and they'd butt back up to 2 millimeters on the end. And that thin section in the middle allows the wheel to have a very good degree of elasticity in the places where it needs the elasticity. But again, you need to have the spokes under nice high tension in order to give it its durability.
So now we're back to lateral truing.
Yeah. Now that the vast majority of the play is out of the spokes, the final truing is going to be what's going to be coming into play.
Okay.
But it's all the exact same thing over and over again. I have attempted to teach numerous different people to do wheel building over the years. And I don't think it directly relates to how intelligent or unintelligent the person is. The number one quality that will determine whether or not you're likely to be able to do wheel building successfully is if you're patient. If you're a patient person, then you're going to be willing to do it the way that it needs to be done, slowly and carefully. I have a friend who's very intelligent, but he knows he's not patient, and so he's given up on trying to do wheel building on his part, and he just trusts it to me. There's a lot of places you can find that also discuss about how to do lacing on the wheel. What we prefer to do with our wheels when we can is what's called mirror image lacing. Again, that information is discussed by Joe Branst in his book, The Bicycle Wheel. Identical lacing is what's most commonly done by wheel building machines and some wheel builders who are
More production oriented.
that might be a good way to phrase it. Yeah, they don't understand the nice fine differences that there is between identical lacing and mirror image. Joe Branst in his book even says that he prefers to do the mirror image lacing so that it's mirror image inside pulling. And what that would do is at these crossover points, this is mirror image inside pulling, at the crossover points the spoke tension is going to be increasing on these spokes and decreasing. So inside pulling, yes. So at this crossover point, it's going to deflect outward and deflect outward. This is where you have the advantage of mirror image lacing. The outward and outward deflections balance each other out. It's probably really just a very fine-tuned differences. I've seen lots of wheels that were built with identical lacing, and they seem to have had good durability. So if proper materials are used, good stress relieving technique is used, then the mirror image versus identical lacing is probably not a critical factor. So when a rim is manufactured, bicycle rims anyway, the aluminum is extruded through a die, and at that point it's a straight bar. Then that straight bar is going to be curled so that it's going to have the final radius. And where's my seam at? It seam's right here. The valve stem hole is here. They're going to then take that curled bar and they're going to cut it side opposite of the valve stem hole, and it's either going to be welded or they'll put a plug inside of it. And at this point, where the seam is the place where there's going to be the greatest amount of variation in tension on the vast majority of wheels. It also would help you to realize whether or not it's a good rim. The better quality rims, the amount of spoke tension variation across that seam is going to be relatively small. Nobody's perfect, but if you find that there's a rim that's got a huge amount of variation across the seam that it's probably a wheel that you can still ride safely, but it's a good indicator that it's a rim that's not built as well as it could have been.
Mm-hmm.
Oh, some people might wonder why they see me tapping the truing arm. This does have friction on it, and I'm just turning this knob a very, very small amount in order to make sure that the friction is overcome. I just tap it. It's only going to probably move it a couple of hundredths of a millimeter. Otherwise, what can happen is when I adjust it, it takes a little while for it to slowly move on its own. I probably should try and address the point, though, of how to know when you've got enough tension on the
Okay.
spokes.
Okay.
Again, it's a subject that's covered in nice detail in the book, The Bicycle Wheel by Joe Brantz. And if you have a spoke tensiometer, that makes it a lot easier. If you don't have a spoke tensiometer, or in our case, the spoke tensiometer won't fit into it because the spokes are too short, you can do what Joe Brantz suggests in there, where you keep slowly increasing the spoke tension until the wheel starts to get to the point where it's collapsing on itself. Taco, you called it earlier.
Right.
And what would happen is right now, as I slowly increase the tension, it doesn't change radically laterally. But if I got to the point where the spoke tension was high enough, then this rim would actually start to collapse, taco style. And it would start to go out of true a lot. So if I'm slowly increasing the tension and I notice that it's starting to go very greatly out of true laterally, I've hit the point where I've hit the maximum tension. At which point I could then go around and I would decrease the tension by reducing the turns on the nipple by at least a half turn, usually 3/4 to 1 full turn per nipple. Just a quarter turn at a time, though.
Mm-hmm.
And very, very strong rims like this, you might would have a hard time being able to get to that point. I have found that with these stronger rims, it could be done, but you'd probably have a very difficult time being able to physically turn the nipples. But that is the method that Joe Brantz suggests in his book. It does work. It'll take into consideration all the factors that you have working together on the wheel, the number of spokes, the diameter of the spokes, so forth and so on, and the rim, of course. The rims that have the lowest amount of ability to handle high tension is wood rims. I like wood rims. I think they're very cool looking, but they cannot handle as high of a tension as a good equivalent aluminum rim, or even a cheap steel rim for that matter. the other rims that are going to be relatively low in their ability to handle real high spoke tension is going to be super lightweight, usually road racing rims, especially if they're low spoke count. So if I've got a super featherweight front rim that's only got 18 holes or 20 holes on it, I would not begin to be able to get as much tension on that rim as I can with this downhill freeride rim. So the wheel now has the final tension on it. I'm not sure what a good way is to describe final tension. We can't measure the spoke's tension with a spoke tensiometer. I basically just get them to the point where it's almost tighter than I'm able to turn it with the spoke wrench. These nice beefy rims will handle very, very high spoke tension. In fact, I get to the point where some of them are too hard for me to be able to turn, but some of the others are still on the lower side, so I'll put a little bit of extra oil down between the nipple and the rim to allow me to be able to tighten those ones that are already a little bit too hard to turn. But what you ideally want when you're done is you want nice, high, hard spoke tension across all the rims. You want it to be radially true, as it is now. And you want it to be laterally true as well. And that should do it.
All right.